Okay, running through the version 4 of the sample problems that you've been sent. Going to go in reverse order. Number 111, I believe. Well, let's start with number 12. No, I'll start with 111. We'll do 111 and 112. Then we'll kind of work backwards through the various pairs and so forth. Okay, you got h of x -5 over the quantity -5x plus 5 squared. Ask yourself, what's the first thing that happens to x? Well, first thing is you multiply by -5, but then you're going to add 5. So you're going to say, okay, -5x plus 5. That would be a good g of x. Something is happening to the -5x plus 5 function. So let g of x equal -5x plus 5. Then ask, what is h of x doing to -5x plus 5? Well, it's doing -5 over the square of it. So that f of x would be -5 over x squared. Thus, when you substitute g of x for x, you get -5 over g of x squared, which is, of course, then g of x being -5x plus 5 gives you what you're looking for. Okay, alternatively, you could say, well, the first thing that happens to x is you do the -5x plus 5 and square. That's a perfectly good function of x. And now you have -5 over that square expression. So g of x is -5x plus 5 quantity squared. That plus sign's looking a little neat, a little ill or something. If g of x is -5x plus 5 quantity squared, then if you plug g of x in for x, you're going to get -5 over -5x plus 5 quantity squared. Now, you do have to really understand how to do composite functions, but the Open Math has assigned you to decompose complex composite functions, functions of this nature. And the functions I could use here are fairly simple, so it's not too hard to do the reverse process, decomposing them, if you really understand composition. I recommend, if you don't understand this, maybe you want to review, run through the, I think section 1.4 assignment, the one on composite functions for practice until you get more comfortable with it. Okay, number 112, you got h of x is quantity 2x minus 5 squared plus 1 over 2x minus 5. Well, you've got that 2x minus 5, it's squared here, and then you take the reciprocal over here. So you're going to let g of x be your 2x minus 5. That's pretty much the only choice you have in this case. So that f of x, well, what's happening? The 2x minus 5 is being squared and then added to its reciprocal. So f of x would be the square of x added to the reciprocal. That way that f of g of x would be g of x squared plus 1 over g of x, which is then the original function. Okay. Now, numbers 109 and 110 are applied rate of change function. You have a temperature that goes from 40 degrees to 100 degrees as your time goes from 3 to 12, and it should be 3 minutes to 12 minutes. Well, you specify down here, you label the t-axis as time t in minutes, and you label that's your little t, that's your temperature little t. The temperature, I'm sorry, that's time little t. The temperature we're going to call big T, and you're going to label the y-axis as temperature big T in degrees. That's the way I recommend doing it. You can choose any letters you want for the time and temperature. If you choose little t and big T, it's going to be easier to recognize what you have when you write out the symbols. So what do? Well, we put this information on a graph. Okay, again, you label little t in minutes, big T in degrees, and you have a point here where t is 3 and little t is 3 and big T is 40 degrees. So here's your vertical line, t equals 3, your horizontal line, big T equals 40, and there's the point that corresponds to this first event. Temperature at 3 minutes is 40 degrees. Second event, little t is 12, time is 12 minutes. and big T is 100. Temperature is 100 degrees. So that big T is 100 along this horizontal line and 40 along this horizontal line, etc. Well, where the T equals 12 makes the little T equals 12 makes the big T equals 100 is here. So you have these 2 points and you want to get the average rate of change. Well, the average rate of change is the change in big T divided by the change in little t. Now it says in the problem, average rate of change of temperature with respect to time. So temperature with respect to time, this with respect to this, always. All right, so you take I recommend using the fundamental triangle here, and you get the change in temperature and the change in time between these 2 points. The change in temperature is the rise of this triangle. Change in time is the run. Rise is 100 degrees minus 40 degrees, that's your change in big T. The run is 12 minutes minus 3 minutes, which is 9 minutes, which is the change in time. And your slope is the change in time divided by change in temperature divided by the change in time. And that's exactly what the average rate of change is. So we could label this. This is your rise, this is your run, and here's your slope. And it's going to be 60 over 9. And I'm going to write that as 60 over 9. Now, your rate of change is actually then 60 degrees because big T is in degrees. And your change in time is 9 minutes because little t is in minutes. So you write the degrees in minutes here. So when you divide this out, you get degrees per minute. Degrees over minutes is degrees per minute. So you're averaging a little over 6 degrees per minute. In 9 minutes at 6 degrees per minute, you change by 54 degrees. You're changing by 60 degrees, so it's a little more than 6 degrees per minute. Okay. Number 110, it's a very similar problem. You have a weight, which we'll call W in pounds, and a time little t. It's this, in this case, in months. You can find the rise and the run of your fundamental triangle, and you could then label the slope if you wish. And the slope would coincide with the average rate of change. Well, then we determine average rate of change is change in W divided by change in T. It's the rise divided by the run, so it's identified with the slope. The slope would be 3.75. The rise divided by the run would be 30 pounds over 8 months. We've got to keep those units in there, which is then divide this and get 3.75 pounds per month. Okay, there it is depicted on the graph. Here it is written out as an average rate of change. Okay. And I hope I'm recording. Yeah, I am. Okay. Numbers 107 and 108 are just problems on this plain old rate of change. And, you know, I'm not sure if I have this whole board on the screen, but luckily it looks like I pretty much did. I'm going to zoom the camera back a little bit. Just you see the all you see here is you see the 110 rate of change line at the top. Okay, so in any case, we move to rate of change problems, and let's make sure this is on the screen. It looks like we're pretty good, but when we get over here, I'm going to have to move the board a little bit. Okay, so if f of -2 equals 2, and you have the 0.01 on the graph of f of x, what's that tell you? It tells you that when x is -2, y is 2, because y equals f of x. This y equals f of -2, this 2 means y equals 2, and the -2 is your x. So you have the point where x equals -2, there's your vertical line, x equals -2, y equals 2. Those two lines intersect here. So that corresponds to this information. This point corresponds to this information. And then you just say you got the 0.01. So you could put the 0.01 on the graph. Here's your y equals 1, x equals 0 is the line corresponds to the y-axis. And I will note that I had a mistake on this. For some reason, I did 0 minus -1 here because I wasn't paying attention, and I got 1 here. So when you look at later videos, if you choose to do so, there's something to kind of watch out for. You're going to see something kind of weird here because I can't go back and change it. Okay. In any case, you get the rise, you get the run. Rise is where you end up, minus where you start, 1 minus 2, which is -1. And the run is where you end up, minus where you start, which is 0, minus -2, which is 0 plus 2, which is 2. There's your delta x, there's your delta y. So your average rate of change is delta y over delta x. And that comes out to then rise, or the delta y, -1, and the delta x, 2. That's -1/2. And of course, that equals your average slope because your delta y is your rise, your delta x is your run. Number 108. What are you given here? Oh yeah, you're given 3 points, sorry. Given 3 points. And they're at 1, 1. Here's x equals 1. Here's y equals 1. So there's a 0.11. 4, 5. Well, here's x equals 4. Here's y equals 5. So there's a 0.45. And 8, 8. X equals 8. Y equals 8. There's your point. So you have 2 line segments between these points, and you can construct 2 triangles. Okay. We asked then, what's the average rate of change between here and here? Well, that would correspond to the rise and run of this triangle, the delta y here and the delta x from this point to this point. Then from 4, 5 to 8, 8, well, here's 4, 5, here's 8, 8. Here's your change in y, which is your rise. Here's your change in x, which is your run. And it's very straightforward. So I've got everything labeled. If you want to see a longer explanation, look at the longer video. Okay, so words happen on the screen, but it's okay. Then we ask from 1, 1 to 8, 8. Well, that's straightforward. Here's 1, 1, here's 8, 8. You got a run and a rise. There they are depicted. Each is 7. You can easily calculate that. So from 1, 1 all the way to 8, 8, your average rate of change is just 1. 1 unit of y per unit of x. You wish you put it that way, but you don't need to in this case. Okay. Your average rate of change here comes out to be 4/3. Okay, it's up here somewhere, delta y over delta x on this triangle. Up here, your delta y and your delta x are 3 and 4, so the average rate of change is 3/4. I've got those on the graph. Okay, and your average rate of change of 1 here. Now the question is the average of the 2 rates of change, this average rate of change and this average rate of change, equal to the rate of change here? Kind of makes sense, it would be, but it turns out that it isn't, because the average of your 2 rates of change is sum of the 2 divided by 2. You add 2 rates, you can divide by 2, so you get the average of the 2 rates. It's not an average rate, but it's an average of the 2 rates, and you find it's 25 over 24. You don't understand the details, look at the longer video. This is not equal to the overall average rate of change. Okay, the third average rate of change, the one from here to here. They're not the same. And then you want to think about why that might or might not be true. I'll say in this case, it's because they aren't. And it comes out to the fact that these intervals from here to here and from here to here are different. So that this applies over a different interval than this does. That's one explanation. You might even think about, okay, if the intervals were equal, would the average rate from here to here be equal to the average of the 2 rates? And it's an interesting question to think about. We're not going to worry too much about it, but I do kind of recommend thinking about it. Now, I pointed to a bunch of stuff over here that I knew I was going to have to move into field of the camera, and I didn't, but all that's over here is, here are your two rates. Here's how you average them, you add them together, divide by 2, here's your result. And it's not equal to the overall average rate of change. Okay. Now, I've got the next one handy here. Trying to do this as quickly as possible so you can get the big idea and then decide if you need to look at some of the other videos. So that was 107, 108. 106 is a little more complex. So complex that I can't find it. Is probably on the back of one of these. Takes me much longer to get this. I'll pause the video for a minute. Now, on this question, you're doing a piecewise function. And I tell you that you have 3 functions here, F1, F2, and F3. And I'm going to zoom this thing back a little bit so we can clearly see the whole board. Hopefully the camera will go into focus. There we go. So F1, F2, and F3 are respectively your toolkit exponential scoring and reciprocal functions. We have 3 intervals, -2, 1, the interval from -2 to 1, -1, 0, the interval from -1 to 0, and 0.5 to 2, the interval from x equals 0.5 to x equals 2. Those are 3 intervals on the x-axis. I've got them color-coded. Then what I want to do is I want to pick, first I want to graph. Now I chose to just graph the first 2 functions. Okay, because the problem tells you, you can choose just 2 of the 3 given functions, or you could choose all 3. Trying to get the camera, come on, up. I want you to go up. That's better. And maybe go down, yeah, you go down the same distance, doggone it. This thing is terrible. It should have a manual focus. Otherwise, it's a great camera. Okay, and let's see if it comes into focus. There we go. A manual focus and a manual zoom. So too much to ask. Okay. We graph the toolkit squaring and exponential functions. F2 is the squaring function. F1 is the toolkit exponential function. Here's a graph of the exponential function. Here's a graph of the squaring function. Okay. Most of it is shaded orange, but you got a little white section down here. And we'll see what happens up to that in just a minute if you don't already know. So I've got 2 functions. Okay. And I choose them to do the squaring function on the first and the last interval, and the exponential function in between. Now, the condition of the problem says, whatever you do in this interval has to be different than what you do in this interval, and what you do in this interval has to be different than what you do in this interval. So you don't have the same function going from one interval to the next. Okay, you can have the same function if as long as it's set on 2 different intervals, as long as they're separated by another interval in the domain of the function. Okay, so and this would be the domain of your piecewise function. That would be the union of these 3 intervals. That's the domain of the function we're going to create. So on the first interval, we just shade whatever part of the first function, the squaring function, applies, and we get from here to here, closed here, open here. And you don't understand that immediately, look at the longer video where it's explained in more detail. And then on this interval, from -1 to 0, we do the exponential function. Open interval, so it's open at both ends, open dots. And then on this interval, we come back to the squaring function. So here's the squaring function starting at this point, ending at this point. That's a closed dot. This is an open dot corresponding to the closed and open ends of the interval. Then we draw it again over here. And note that every time I draw a graph, I'm including the construction lines. That's no brainer. You always want to do that. Label the construction lines and the boundary lines. That's always. Okay. No, I didn't bother labeling them here, but you know how they're labeled. I think everybody knows how they're labeled. So now I've just graphed the parts of the function. Now the white is the part that corresponds to the squaring function. This part and this part, and the blue is the little segment that corresponds to the exponential function. Without the construction lines, here's kind of what it looks like. But with the construction lines, you can tell a whole lot more. But here I've labeled the points, the endpoints of each segment. And there we have it. Standard way of notating this is as you see here, and that's what you've seen in open math. So I don't need to explain that right now. It's kind of explained in the longer videos. As for the domain and the range, well, the domain I've already mentioned. It consists of all the x values of which we've shaded y values. Notice that the interval from 0 to 0.5 is not part of the domain because nothing is shaded above there because that wasn't specified. Okay. The range, now what's the range? It's a set of all y values. What's the lowest y value you see in the graph? Well, it'd be 1/4 corresponding to this point that you should know well on the graph of the squaring function. And it goes continuously from here all the way up to 4, just because of the squaring function. So we have y values that go all the way from 1/4 to 2, including 1/4, but not 2. Again, if you want a longer, slower explanation, look at one of the longer videos. Okay. You have 2 sets of videos following this. One is a little briefer, the other is a bit longer. One's pushing 3 hours, the other is about an hour and a half. And it's, you know, the hour and a half is a summary of what I did on the 3 hours. The longer set of videos, or the set of longer videos is the first thing I did. And you can tell that by just looking at what's there. Okay, so there it is. There's your piecewise function. And people do sometimes find this challenging. All right. That's that board. Now, 104 and 105 are inverse functions. And I have 105 right here. Well, I'm not sure I see 104. There it is. I'll do 104 before I do 105. Okay, 104 and inverse functions. Now, this doesn't turn out so well with the numbers you have in the graph because some of the estimates are awful close to others. And it doesn't show up all that well. But I'm going to go over it anyway. So you have first a function. You're given that. Now I don't remember if you're given, yeah, I think you're given the coordinates of 3 points on the graph. Be negative 1.6, 1.6, negative 0.7, negative 0.3, 0.7, 0.7, 1.5, 1.3. We construct, and it says construct, use the construction lines it would use for the reciprocal function, which has the red dot in the middle, still 4x4 rectangle. So we draw the construction lines and label them. And there's x equals -2 here, x equals 1 here, x equals 0 here, x equals 1/2 would be this one, x equals 1, I've labeled all the way up here, and x equals 1, well, that we use that, but x equals 2 is here. Now, it got run together a little bit. If you want, you can watch me construct this step by step in the longer videos. The third set, the longest videos. Okay, well, we construct this, we label all our construction lines. The coordinates are points on the table. Now I read them off of the table. They weren't given on a table. Oh no, what's going on here? This thing is still apparently recording, but there's no video. Now, why did the video choose to stop? Well, looks like I'm going to have to troubleshoot this. So I'm going to have to stop this video right here. Then I'm going to have to go back and look at where I stopped. Look at where the thing stopped recording. It's a little bit of a pain, but the video will continue on another one as soon as I get this sorted out.